So let's reinforce our understanding of categories by solving some problems. The first problem, show that the identity arrow is an isomorphism for every object A of category C. So recall the definition of an isomorphism. An arrow is called an isomorphism if you can find an inverse arrow. So identity A inverse is equal to identity A, and in fact we see that this is the case because identity A inverse, which is identity A circle identity A is equal to identity A. And so if we treat this as identity A inverse, then we're getting this, and we also get identity A circle identity inverse equal to identity A. Both these come from the identity axiom. So just to write this down nicely, I'll say set identity A inverse equals identity A. Then we have these things which establishes that identity A is the inverse of the identity. Okay, so that was easy. Let's try something a little more interesting. So for each object, A of a category C, let ought A equals F, the arrows from A to A, such that F is an isomorphism. Show that ought A is a group. Okay, so before we go into this, let's recall the definition of a group. It is a set G together with an operation, a binary operation dot, such that dot is associative, i.e. X dot Y dot Z is equal to X dot Y dot Z for all X, Y, Z in G. Then for every object, for every element X in G. Oh no, but first I should state the identity axiom. There exists identity in G such that X dot identity is equal to X, and that is also equal to identity dot X for all X in G. And the third axiom is the axiom of the inverse. So this is the associativity, identity, and inverse axiom. For every X in G, there exists X inverse in G such that X dot X inverse is equal to identity G, and that's also equal to X inverse dot X. So these are the axioms for a group. And so what we have to show is that this set of arrows is a group. Let's say with the binary operation under composition. So let me just make that clear. And so we just need to check these axioms. So now the solution. Of course, composition is associative by the associativity axiom for categories. And then there exists an identity which is identity sub A. By the identity axiom for categories. And thirdly, the existence of an inverse. Well, that comes from the fact that we have defined it to be a set of isomorphisms. Every F being an isomorphism admits an inverse. So that's it. The two axioms of associativity and identity follow from the axioms of a category, and the third axiom of inverse just comes from this definition of ought A. Okay, the third problem. Consider the category with two objects, which I'll call A and B, and three arrows as below. So let me show you what the arrows look like. So we have an object A, we have an object B. We must have an arrow identity A from A to A. We must have an arrow identity B from B to B. And now there's only, and we will have, let's say, an arrow F from A to B. Okay, so show that F is a monomorphism an epimorphism but not an isomorphism. Okay, so just pause your video and think about this. You need to maybe go look up the definitions of monomorphism and epimorphism and isomorphism, and then try to solve this problem. If not, you can watch me explain the solution. This is just a matter of definition. So recall what it means for F to be a monomorphism. So F is a monomorphism means that to show that F is a monomorphism, we need to show that for all objects C of the category C and arrows, let's say G and H from C to A, such that F circle G equals F circle H, we have G is equal to H. But in this category, there is only one morphism between any two objects. There's only one morphism from A to A, there's only one morphism from B to B, there's only one morphism from A to B, and actually there are no morphisms from B to A. So there's at most one morphism between any two objects. And so this conclusion here is trivially satisfied. So no matter what kind of composition you have, since there's only one morphism from any object C to A, the G equal to H is vacuously true. So G equals H holds because there is at most one arrow between any two objects. In C. So that shows that F is a monomorphism, and the same argument also shows that F is an epimorphism. Now, is F an isomorphism? So recall the definition of isomorphism. For F to be an isomorphism, we would need F inverse from B to A such that F inverse circle F is the identity of A and F circle F inverse is the identity of B. But don't even worry about these conditions. There is no arrow from B to A. So F inverse cannot exist. And so that means that F is not an isomorphism. So this again runs contrary to our intuition from set theory that if a function is injective and surjective, then by definition it's bijective. And so an arrow is an isomorphism if and only if it is an epimorphism and a monomorphism. But here we have an arrow that is both an epimorphism and a monomorphism, but not an isomorphism. Okay, problem 4. Show that the inclusion map J from Z to Q is an epimorphism in the category of rings. Now, before solving this problem, let's just recall a few things about rings. So recall that a ring consists of two binary operations, addition and multiplication, and we have that ring under addition is an abelian group, ring under multiplication is a monoid. In particular, we are assuming that rings have a multiplicative unit. Okay, so rings have a unit. So it's the identity of this monoid is the multiplicative unit. And then these two operations talk to each other via distributivity. This is a ring, and so in the objects in the category of rings are in the category ring are rings, and morphisms are ring homomorphisms. So a ring homomorphism if it is a group homomorphism from R plus to S plus and a monoid homomorphism from R dot to S dot. Okay, I'm just writing this down somewhat informally, but an important point is that F takes the multiplicative unit of R to the multiplicative unit of S. So this is a very important assumption that we make when we define the category of rings. Okay, so now you can pause your video and try to solve this problem. It's actually quite interesting. So here's what I'm going to prove. So suppose F and G are homomorphisms from Q to R. Then I claim that F is F is just equal to G. So let's just see. So F of a rational number A by B is equal to so A by B is A times 1 by B. And now because F is a homomorphism of the multiplicative monoid, what this means is this is F of A times F of 1 over B. But A here is an integer. If A is a positive integer, then A is 1 plus 1 plus 1 plus 1. And so F of A is A times F of 1, but F of 1 is 1 of R. So, and if A is negative, then, well, it's the inverse, so you can again write this into that F of A is A times 1 of R. So this is A times 1 sub R, F of 1 over B. And then I can write this as, well, for the same reason, this is equal to G of A. There's no difference between F and A. So if F of A is forced to be A times 1 of R, G of A is also going to be A times 1 of R. And F of 1 over B. Now this is equal to G of A over B times B, F of 1 over B. And now I can write this as G of A by B times G of B times F of 1 over B. Okay, let's just draw use a 2-column format here and move over to the other side. So now this is equal to, now G of B, as we've seen before, this is B times 1 sub R. So this is G of A by B, B times 1 sub R, F of 1 over B. And so I can write this as G of A by B, and then this is F of B times F of 1 over B. And that's G of A by B, F of B into 1 by B, which is G of A by B into F of 1, which is G of A by B into 1 sub R, which is just G of A by B. So what we see is that there's only one ring homomorphism from Q to any ring R. They are all equal. Okay, and so now automatically this means that J is an epimorphism. Indeed, given G and let's call them F and G from Q to R, such that F circle J is equal to G circle J. Well, even without this condition, we have F equals G, because we have F equals G without even this condition. And so that finishes the solution. And this is very interesting because J is not a surjective function, and yet this is an epimorphism. In fact, J is an epimorphism and a monomorphism. Because it's an injective function, it has to be a monomorphism, and we just showed that it's an epimorphism, but it's not an isomorphism. The next problem explores a certain duality that you will see throughout category theory. Each definition in category theory has a dual, and basically the dual of a definition is the same definition in the opposite category. So just to make that explicit, let me write down this problem. So show that F, an arrow from B to C in a category, is monic if and only if F now can be regarded also as an arrow from C to B in the opposite category. Recall that the opposite category is the category with the same objects, but the arrows from B to C are thought of as arrows from C to B in the opposite category. So you should try to just unwind the definitions and solve it yourself. Otherwise, just watch me solve it. So let's just prove, firstly, suppose f is monic. And I want to prove that this is epic. So take any two arrows, G and H, from B to A, and consider such that we have that F circle, no, G circle F is equal to H circle F, and this is the composition in C op. Then F circle G is equal to F circle H. This is composition in C. And since F is monic, in CBC, what we have is G is equal to H in CAB, which is the same as saying that G is equal to H in COP BA, and therefore F is epic. The other statement can be done given a similar proof, that if F is if F in COP is epic, then F in CBC is monic. And I'll leave that for you to work out if you feel like.